Okay, so the binomial, it says, suppose that 51% of U.S. residents are women. In a random sample of size 1,000, what is the probability that fewer than 500 women are selected? Use the binomial and the normal model, normal approximation. So binomial, okay, so if it's a binomial, what is n? How many people are we asking? 1,000. And what is p? The probability of success. 0.51. So Q is what? 0.49. And X is the number of women. Success is choosing a woman, right? Because the probability is asking about the number of women selected. So we want to know what's the probability that X is less than 500 women. Okay, so this shouldn't take long. We can just do binomial CDF. Binomial CDF. It's a less than probability. Now, what does the binomial CDF command actually find? Does it find just less than probabilities? It finds less than or equal to. This finds less than or equal to probabilities. We just want a less than probability. So we have to think about this a little bit. We're going to type in our n, which is 1,000, the number of trials. Our probability of success, 0.51. And then our x value, what should it be? It's not 500. It's 499. Because we have to include, it's the or equal to one. So you can't ask you can't ask 499.5 women, okay? It's less than or equal to 499. Okay, so do that in your calculator. Tell me what you get. 0.2532? Okay. So now we're going to change this to normal. Let's just change it. Let's just not pay attention to the rules and just use a normal. Okay, change it to normal. So if I change this to normal, the mean is going to be n times p, and the sigma is going to be the square root of npq. So n times p is 510, okay, and n times q, or square root of npq, you've got all of them right here, so just type them in and take the square root. Round to the nearest whole number, please. 15 or 16? It's 16. Okay, so that means that x is now approximately normal with a mean of 510 and a standard deviation of 16. And so I'm going to draw my picture. Here's 510, 526. And then my next standard deviation is 542 plus 16, 558. Subtract 510 minus 16 is 494, minus 16, 478, minus 16 again, 462. So there's my normal distribution, and I want to now know the probability that x is less than 500 using my normal. So 500 is like right here, and shaded this way. So now I'm going to do normal CDF. And what's my lower bound? What's on the left of this? Negative infinity. And the upper bound, 500. My mean is 510. And my standard deviation is 16. So again, this was lower bound, upper bound. Mu and sigma are my commands that I type in, and it prompts you if you've got the right kind of calculator. And we use the shaded part to tell us lower bound. If you're shading all the way over here, it's always negative infinity. If you're shading up here, it's always positive infinity. And what do you get when you do that? 0.2660. Okay. So I have a question. Were these two close to each other? 0.26 and 0.25. Is that pretty close? Yes, these are close. These are close. Is that good or bad? It's good. Good. That's good. Okay, why is that good? Because I'm trying to use the normal to approximate the binomial. If it's a binomial distribution, the binomial distribution is the best way to go, okay? But sometimes it's okay to use a normal distribution, okay? In this case, it must have been okay because the probabilities are close. Okay, now I just want you to, look at something. What is n times p and n times q in this problem? Well, we already found n times p was 510. N times q is 1,000 times 0.49, which is 490. Are they both greater than 10? Okay, both greater than or equal to 10. So that's why it's okay. They're close, okay? So that's why they're close, because n times p and n times q were greater than 10. This condition is something that you should check before, okay? You're not going to do problems both ways. You're either going to do it binomial or normal, okay? Normal is actually more work because you have to change it into normal, okay? So binomial is the best way to go. But sometimes if your n is too big, you have to change it to normal. All right, so now we've got one more example to go through, and this is the same thing.